Hello, and welcome back to the fifth test of this terrain engine, texturing and shading. Today I will be going over the problem of texturing voxel terrain with the triplanar projection, as well as the issue with normal height-based sampling, and I will also be going over smooth shading, as well as bump shading and tangent space with normal maps. Beginning here in the paper, it opens by talking about the typical procedure of using some right and forward directions, which are X and Y in the paper. However, in the code you will see it will be X and Z. The problem with using these directions for sampling textures is that the samples themselves become very stretched as the terrain slope increases. Voxel-based terrains have a much harder problem as their terrain slope can actually encounter an infinite slope. The paper also mentions that this form of projection reverses the headedness of the tangent frame when surface normals face downward, and that problem is demonstrated here in the paper, and I have also recreated it here in the code. The paper goes on to offer the solution of generating multiple sets of texture coordinates by projecting the vertex position onto multiple planes. This is a technique known as triplanar projection or box mapping. Triplanar projection generates three pairs of texture coordinates SXTX, SYTY, SCTZ, and these coordinates are mapped to planar faces along a cube. One thing to note about computing these coordinates is that the axis subscript denotes the direction of the normal of that plane. So for example, here in the paper, the coordinate pair SXTX is computed by projecting the vertex onto the YZ plane, where Y and Z map to S and T. Similarly, the SYTY maps to the XZ plane, and the SCTZ maps to the XY plane. One thing I would like to bring up again is that in this paper, it uses the coordinate system of XYZ XZY instead of XYZ. So when we get to the code, the computations and usages of SYTY and SCTZ will be swapped. Now with the three sets of texture coordinates, one or more texture maps may be sampled at three different locations. The combination of these samples should be blended together in such a way that stretching caused by projection of one plane should not be visible. The paper proposes that calculating X, Y, and Z blend weights can be done with these three equations right here. They're all the same except that they swap out one axis for another. The equation takes the difference between the interpolated vertex normal and delta. Delta is some real number between 0 and the square root of 3 over 3. And the reason why this is the cap for delta is this is the largest contribution a normal vector may have along any one coordinate. The resulting difference is then maxed with 0, such that if there was a negative value here, there's just no contribution given for this particular coordinate. And then the resulting value is then raised to some positive integer m. After the weights are calculated, they are then normalized by taking the blend weight in one axis and finding its proportion of the total blend weight. Once normalized, the triplanar sample C can be calculated by using this equation, which multiplies the blend of one axis by its sample and sums each of the resulting planar samples together. As noted below, Cx, Cy, and Cz are just texture sampling functions. The previously mentioned variables delta and m are fairly important to the final blend. Delta controls how much one texture map shows up over another. The larger values of delta create larger plateaus on the cube faces, which cause samples with very small normal contributions to not be included. The exponent of m determines how fast transitions between texture maps is as the dominant component of the normal moves along curved surfaces. When m is larger, this produces a sharp transition over small angles, and when m is smaller, this produces a smooth transition over large angles. And then the paper shows a little example here of variable deltas and variable m's. with sharper transitions and more or worse blending. So now, similar to the paper here, I'm going to show the implementation of triplanar projection, where the right texture map, or your main texture map, gets used on your lateral faces, and then your negative up face, and then this texture map gets used on your positive up face. Now at the end of this, I will go over the actual shader files once we get closer to the tangent space mapping. But for the time being, as you can see, the texture stretching problem has been eliminated using the triplanar projection technique. I would briefly like to mention that I will not be going over the material specification and resulting material sections of the paper. The reason for this is this section is really talking about the end of a terrain engine, right? Where like you have an actual tool that an artist can boot up, they can set some parameters, they can load some assets, and go to town creating really magnificent terrains. For the time being, and I'm not opposed to creating that technology, it's just for the time being, I would like to get the technique of the shading and the texturing for the terrain done. And then whenever I come back and do a second pass on this terrain engine, I can go in and really look at specifying texture maps. And the paper did, I'll just, while I'm talking about this, mentioned a very interesting encoding technique where you can poison or just specify various textures to be used at voxel coordinates, which I am very interested in implementing. But again, for the time being, this is just going over the texturing and shading aspects. Alrighty then, so let's talk about tangent space and bump mapping. This section delves right into the math that deals with what we're trying to do here. Bump mapping requires that we have information about how texture maps are oriented in two-dimensional tangent space for each vertex point in a triangle mesh. Here, SP and TP are two functions which map a vertex point P to the texture coordinate ST respectively. Orientation of the texture maps induced by SP and TP are quantified with the below inequalities and equations. The first two state that the divergence of SP with the tangent vector is at least 0, and the divergence with TP and the tangent is 0. The second two are the inverse, where the divergence of SP with the bitangent is 0, and the divergence of TP with the bitangent is at least 0. If this is confusing for you, you are not alone. I actually went off for a couple days just looking into divergence and flux-eons. All in all, really what these equations are stating is just that the dot product of the tangent vector over the function SP of the triangle mesh should always have some similarity. However, the tangent vector and TP must be perpendicular. The opposite is being stated for TP and SP with the bitangent. The reason for this is that it produces the ideal tangent field, which would be a continuous function over the entire surface. Unfortunately, some topologies are just impossible to produce a continuous function for, so we must abandon this ideal function and work with the tangent fields already induced by the triplanar projection. These tangent fields are shown here. And in case you were wondering more about divergence and tangent fields, this is really what it's saying, that when it's greater than 0, it's pointing outward, less than 0, it's pointing inward, and then when it's at 0, it's perpendicular. This should kind of help you visualize these equations right here. Now let's move on to the TBN matrix and calculating T and B with the triplanar coordinates. For any particular vertex position with a unit normal n, the tangent vector is found by projecting the normal vector onto the three planes previously mentioned, yz, xy, and xz, and then rotating these projections 90 degrees counterclockwise. So for example, if we had some normal vector and we projected to the yz plane, then we have the vector 0, y, z. Then, to rotate this vector 90 degrees, you swap the first axis with the negated second. So the example of 0yz rotates to become 0 negative z y. This will produce a tangent vector that, when crossed by the normal vector, will produce a bitangent vector. It is these three vectors that form the basis of the TBN matrix, or the tangent-bitangent normal matrix. The TBN matrix itself is designed to move vectors from tangent space into object space, as illustrated here. However, since the shading calculations that we will be performing are in tangent space, we will want a matrix that moves from object space into tangent space. This is achieved rather trivially, as the TBN matrix is orthogonal, thus its transpose is its inverse. By using the transpose of the TBN matrix, we get a matrix that will move out of object space into tangent space. It is in this space where we will be doing all of our shading calculations when using bump mapping. And now we are finally able to move into the last part of the paper, the shading section. In this section, the paper describes how to incorporate the triplanar projection coordinates with the tangent space bump mapping technique. The shading technique that is used will be the Blin-Phong shading model. When the terrain is rendered with smooth shading, it is only the triplanar projection and Blin-Phong that is used to determine the final color sample of the terrain. When bump mapping is used, the tangent space calculations are referred to resample the fragment normals based on normal maps, and these samples are then fed into the Blin-Phong equations. And just in case you're unfamiliar with Blin-Phong or the details of the equation, it is your final color sample, C, is the sum of the product of the ambient color and the ambient intensity with the product of the sum of the portion of diffuse and specular lighting contributions with the direct intensity. In the above equation, the ends is what will be resampled when we do the bump mapping. There's really only a handful of things that need to be mentioned about this equation, and it's your L and V variables. L is defined as the unit vector pointing from some vertex P to the position of the light source, and V is the unit vector pointing from some vertex P to the position of the camera. Generally, the camera will always be represented as a position in some regard, so the vector V may be calculated as V equals the camera minus P. However, the light source is not always so simple. In the case where there is a physical position of the light source, then the value of L can be calculated in the same manner to V, where it's the light position minus P is L, so as it says right here. However, in the case where your light source is just a unit vector that describes the direction of the light, then to calculate L, it is just the negated value of the unit vector. And one more thing to mention is that L and V in these equations are in object space, so they must also be multiplied by the transposed TBN matrix so that they are in the proper tangent space when doing the bump mapping. Now, aside from the normal samples themselves, the only thing that really changes when working in tangent space with the shading is how the quantities n.L and n.H are computed. Since the texture samples of each plane are in its own tangent space, we must first blend the samples independently and then combine the blended coordinate contributions. And then here at the end of the paper is another render that shows the difference between the smooth shading and the bump shading. Now, like I promised, let's actually delve into the shader and take a look at the code behind the scenes. To start, we will begin in the vertex shader. This is a fairly standard shader. The VBOs only hold positions and normals, since the UVs, tangents, and bitangents are generated procedurally. For output, we will be outputting the vertex as local position and the vertex normal as normal. And we will also output some light to vertex and vertex to light calculations in the two tangent spaces. One thing I did forget to mention is that we are only interested in the tangent fields along the XZ and the XY plane. The reason being is that the tangent field for XZ is the same as YZ, since these are both the lateral faces of the cube. As far as uniforms go, we just specify the direction of the light as the light normal, the physical position of the camera, and then the view projection matrix. Here, object to tangent is just a helper function that takes the TBN matrix basis vectors and returns the transpose of them. And then now here in main, nothing crazy happens. This is standard OpenGL stuff or GLSL stuff. And then here, the XZ tangent and the XY tangent are calculated using that projection to the plane and rotating 90 degrees. And then the respective bitangents are just the cross product of the n and the tangent. Then after we have the TBN vectors, we will create our two TBN matrices. And then from these two TBN matrices, we will move our vertex to light and vertex to camera variables into their proper spaces. Now the fragment shader is a bit more involved, but here are all the in variables that we just output, and then here is the out for the color. And then this is the structure we will be using for texturing. As you can see, there are two of them, one for the lateral faces and the negative Y face, and then one for the positive Y face. This is the that light direction, and then this is used for something I'll explain in a bit. So I will start here in main, and to begin, you get that interpolated vertex normal by normalizing the normal, or the vertex normal that comes in. This will interpolate it across the fragment as the fragment shader runs. Then you perform the triplanar projection here, where you get the SXTX, SCTZ, SYTY coordinates by doing that cubic projection. And then we also want to calculate a vector that will essentially flip the S texture coordinate when the normal is pointing in the reverse direction. Then we also sometimes have to use that inverse Y, so we just have a variable that records that for later use. And then right below that is the blend parameter. Now this 0.5 here, this is the delta, and then what this is doing is raising it to that M parameter. So this is essentially saying it's the absolute value of the normalized interpolated fragment normal minus delta, and then we're going to take the, or really what we're doing is clamping that between 0 and 1. The paper, I think, uses the saturate function. But after we get that value, we will raise that value to the fourth power, and then we will normalize that value. So now that we have the three texture coordinates and our blend weights, we will go ahead and use these to calculate the actual triplanar projected texture color sample. And to do that, we are going to take three color samples, one on the X, one on the Z, one on the Y. And this diffuse sample just simply switches on the 0 or the 1. If the texture coordinate is 1, this is the top, so the positive Y. Everything else, positive, negative X, positive, negative Z, and negative Y, those will all be given a 0. And those will be using the lateral texture. This is kind of a hack from not doing the material specification. That section goes into how you handle switching between multiple different primary and secondary textures. But for the time being, like I said, I wanted to get the technique working, because really this technique will work with the material specification. You just replace the textures and the sample information and make it more dynamic in its accessibility. However, for now, this hacky solution works to demonstrate the technique. After we get the X, the Z, and the Y, we go ahead and multiply them by their blends, and then we sum the triplanar projected color sample together. So first we're going to look at smooth shading, since this is the base of the bump shading, which uses the texture mapped normal samples. And the code for smooth shading is right here. As I said, it's just blend Phong, and this is the blend Phong equation in case you needed it again. So to begin, we calculate the ambient by the light color and the ambient intensity. The diffuse is gotten as the dot product between your fragment normal and that L value, but since L in this case is just the negated light normal, there's really nothing more to do here. And then we just make sure that this number is greater than 0, and if not, we just clamp it. For specularity, it's kind of the same thing. We will make this our light direction, and we want to normalize the vertex to camera for the same reason that we normalized this down here. We want to interpolate across the fragment between each vertex. Then to calculate the halfway direction, we will normalize the light direction. Well, that's interesting. With the view direction, and then the specular component, or the specular contribution, is the dot product of the normal with the halfway direction, and then, like the diffuse, we clamp it to 0. After we have our ambient, diffuse, and specular components, we go ahead and add them all up, or add the sums of the products, and we get the ambient plus the diffuse times the specular to the power of 32 by the light color. And this component right here, it's completely up to you. You just change it based on your scene. So now looking at bump shading, we will begin by normalizing our tangent space variables. And again, the normalization is done for the same reason we want to interpolate across the fragment. An ambient is calculated in the same way, but as previously mentioned, the diffuse and specular components are calculated in their own tangent spaces, so the x, y, and z components need to also be calculated in their own tangent spaces. For actually fetching the normal sample we'll be using, we grab the normal sample based on the same texture index switching, and then we will normalize it or move it into the range of I believe this moves it into 0 to 1, the 0 to 1 range. Now, after we have gotten our new normal samples, we will go ahead and perform that dot product on the n.l, and then we clamp it from 0 to 1 just to make sure that it's within that proper range. We do this for x, y, and z, and then we go ahead and multiply the blend weights by the coordinate contributions for the diffuse, as well as we do the same kind of operation for the specular variable right here. Then at the end, just like with smooth shading, we just add the ambient with the diffuse and speculars product with the light color. So one thing that I did forget to mention, but I'll talk about it now before the gamma correction, is this high fidelity boolean here. It's used when LOD is 1 or 0. The reason being is that as things get really far away, you have a lot of different, not necessarily tricks, but a lot of things that help to mask other things that are far away. Saying things a lot here, but it's really arbitrary what it can be. It could be something like fog of war, other atmospheric effects. It could be really large buildings like occluders. It could be a number of things that, as you get far away, kind of reduce the overall scene complexity. So one of the things is here, as things get really far away, we just kind of go to smooth shading. Not necessarily because you can't see the bump mapping or the bump shading benefits far away, but because they actually kind of do get distracting, but they also don't provide a lot of detail to what's really going on. Like, yes, you can see the detail far away, but it's just that. It's just detail. It stops there. There's really nothing more you can decode from it. You can't tell it's the detail of what exactly. So when they get really far away, we just smooth shade, and it also saves a lot of texture fetches. You got to think, when you're doing the bump shading, there's 3 samples as well as your normal triplanar, which is another 3 samples. So reducing the overall number of samples taken is greatly going to benefit your frame rate as well. And one more thing I would like to mention before talking about gamma correction is parallax mapping or parallax occlusion mapping. If you don't know what the technique is, I'm not going to explain it too much. It's kind of just the natural complement to bump mapping. However, due to the unregulated terrain topologies that can be produced with voxels, it's best you don't use POM. I did get it working to the best that it was going to. The issue is that when you have really dramatic surface changes between fragments, parallax occlusion mapping really starts to just break down because it warps the fragments around it. So you kind of get this really melting looking terrain and really really curved parts of your surface. So unfortunately, you can't parallax map with this. It saves you a lot of texture fetches, which is a good thing, but it will just not work well. So stick with smooth shading and bump shading, and your overall terrain should look pretty decent. So now that we have our color sample and it's been illuminated, we just go ahead and gamma correct. And gamma correction isn't really anything specific to this. It just has to do with the color spaces that textures are usually created in. They're not the color space we want to work with. So when we load that texture into OpenGL, I believe we use like an sRGB or an sRGB-A flag, and then OpenGL goes ahead and it manipulates that data, and then we can go ahead and come into the shader and apply our gamma correction on that corrected color data that OpenGL has. But that should just about be it. Thank you all for sticking with me through this terrain engine endeavor. This was a bit of a shorter one. There is some side work being done on a parser. I'll be moving next into doing animation or looking at the animation system, because that's really the last thing the framework doesn't have. So it's one of the last group of question marks that need to be erased before the entire framework can have an overhaul and its linkages. However, I will have more to come on this later. It's pretty interesting stuff. The DDL. If you don't know what DDL, OpenDDL, OpenGEX, they're also by Eric. They're pretty interesting. A bit over cumbersome in some places, over engineered. However, I really think they are the only transmission formats that really get the job done. So stay tuned, more to come on that. However, thank you guys again. Hope you have a good rest of your day, night, whenever you're watching this, and enjoy the terrain fly through of the fully textured transvoxel terrain.